Hi everyone, and welcome back to the MCAT A series of lectures in physics. In the previous lecture, we talked about gases. This lecture instead will focus on fluids. A fluid is simply something that does not have a fixed shape. Therefore, gases are included in this, but it also includes things like liquids and other states of matter like plasma, which are outside the scope of the MCAT. As I have already discussed gases in great detail, I shall focus this lecture instead on liquids. To begin the video, I shall define what is known as density, which is an intrinsic property of a substance. What is known as specific gravity will then be discussed, which describes how big or small the density of a substance is relative to water. I will then move on to discuss buoyancy, which is the force exerted on an object that is placed inside a liquid. Archimedes' principle will then be introduced, which describes how that buoyant force relates to both the weight of the object and the density of the liquid. Pressure, more specifically hydrostatic pressure, will then be discussed, which is simply the pressure exerted by a fluid due to the force of gravity. Then I shall introduce an equation that allows us to calculate the pressure at a depth h within a liquid. A property of a fluid known as viscosity will then be discussed, which is a measure of the internal friction within the fluid. I will then describe what happens to the speed of a fluid when it goes through a smaller cross-sectional area. This will be done by using what is known as the continuity equation. Turbulence, which is caused by chaotic motion within a fluid, will then be discussed in particular at high velocities. I will then discuss how certain small insects are seemingly able to walk on water due to what is known as surface tension. I will then discuss what is known as Bernoulli's equation, which is simply the conservation of energy for a fluid. Then I will describe what happens to the pressure of a fluid when it flows through a small constricted area of a pipe. This is known as the Venturi effect, and an application of this effect will be considered with pitot tubes. I will then finish this video by considering fluid motion within our own bodies. For example, various characteristics of the circulatory system will be considered. You may have heard the trick question before: what is heavier, a kilogram of feathers or a kilogram of steel? Of course, they both are equally heavy. They both have the same mass of 1 kilogram. If we are to have 1 kilogram of steel and 1 kilogram of feathers, then we must have a very large number of feathers. In other words, the volume of the feathers must be very big. In other words, if we want the mass of steel and mass of feathers to be the same, we must instead have the volumes being different. Density takes this into account. Let's assume that we have an object of mass m and volume capital V. The density of that object is defined as the mass of that object divided by its volume. To represent density, we use the Greek letter rho. Rho is equal to m divided by capital V. As density is defined as mass per unit volume, it has units of mass per unit volume. In other words, kilograms per meter cubed. Density is said to be an intrinsic property of a substance. That means that it is not dependent upon how much of that substance we have. The density of, for example, gold is always the same no matter how much gold we have. Therefore, going back to our example of 1 kilogram of steel and 1 kilogram of feathers, although their masses are the same, the volume of the feathers is much larger. Therefore, its mass divided by volume is much smaller. The density of feathers is much smaller than the density of steel. The concept of density will be very useful to us when we consider the idea of buoyancy in a later slide. Recalling our definition of weight, remember weight is a force. The weight of an object is equal to the mass of that object multiplied by the acceleration due to gravity small g. As we shall find out when discussing buoyancy, it will be very useful to replace this mass by density multiplied by volume. Since density is mass divided by volume, mass is density multiplied by volume. This may seem like a random step to make, but it will become quite clear why I considered this when we discuss buoyancy. To finish this brief introduction to density, I would like to now consider what is known as specific gravity. It turns out that the density of water is 1000 kilograms per meter cubed. We can write this even simpler because 1000 kilograms per meter cubed is the same as 1 gram per centimeter cubed. I encourage you to check this in your own time. Therefore, we can define the specific gravity of a substance, capital S, capital G, as the ratio of the density of that substance to the density of water. In other words, it is the density divided by 1 gram per centimeter cubed. In other words, if a substance has a density of 3 grams per centimeter cubed, its specific gravity is 3. Its density is 3 times that of water. Similarly, if its specific gravity is 0.5, that means its density is half that of water. Introducing the concept of specific gravity allows us to easily visualize if the density of that substance is large or small by comparing it to the density of water. Now I would like to consider what is known as hydrostatic pressure. The hydrostatic part of that statement simply means that the liquid is at rest. The liquid is not moving. Of course, the particles within the liquid could be moving, but overall there is no bulk motion of the liquid. The liquid is not moving, for example, from left to right. I have already briefly discussed what pressure is in relation to gases and other substances. Pressure is defined as the force per unit area. As it is the force per unit area, it has units of force per unit area. It has units of Newton per meter squared. Again, to save us time from writing Newton per meter squared down all the time, we instead write Pascal. 1 Pascal is equivalent to 1 Newton per meter squared. As I just mentioned, I have already discussed pressure with regards to gases. I described how the pressure of a gas relates to the force exerted by the gas on the walls of its container. I also described atmospheric pressure. As there are many particles above our heads, they are exerting a force on our body. Those particles have a mass associated with them, and therefore they have a weight associated with them, and therefore they are pushing down on us. Liquids, of course, have a higher concentration of particles. In other words, they have a higher density. Therefore, if we consider an object submerged or partially submerged in a liquid, its pressure must be greater than that of atmospheric pressure. More precisely, its pressure is given as follows. Let us consider an object which is at a depth h within a liquid. As the liquid and the container itself is within the atmosphere, there is still the particles above the liquid pushing down on the object. There is still atmospheric pressure. Therefore, the pressure on the liquid is equal to the atmospheric pressure plus the pressure caused by the liquid. The pressure caused by the liquid is equal to the density of the liquid ρ multiplied by the acceleration due to gravity g multiplied by the depth h. Therefore, the pressure on the object in the liquid has increased by a factor of ρgh. This is of course a very simple formula, and a typical MCAT question could simply be that you are given all but one of the quantities and you have to find the remaining quantity. Unfortunately, the MCAT goes into more details with regards to liquid pressure. For example, what is known as Pascal's law can also come up on the MCAT. Pascal's law, which is sometimes known as Pascal's principle, states the following. Any pressure change within a liquid is distributed throughout that liquid in such a way that there is the same pressure change everywhere. In other words, any local pressure change in a liquid gets distributed to the entire liquid. To understand this better, let's consider the following situation. Let's say we have a liquid of a certain density ρ that is contained within a complicated container such as this. We have a container on the left with a piston above the liquid. We have a small narrow opening through which the liquid can flow, and we have a much larger container on the other side, again with a piston above the liquid. Let us assume that the cross-sectional area of the piston on the left is a sub 1 and on the right is a sub 2. Now let us push down on the piston on the left. In other words, let's apply a force F sub 1 on that piston. Doing so will of course change the pressure within the liquid. We are applying a force to the liquid and therefore applying a pressure. According to Pascal's law, this pressure must be distributed equally throughout the liquid. This downward force on the piston on the left has caused an upward force on the piston on the right. Remember, pressure is equal to force per unit area. Therefore, since the pressure is equal everywhere in the liquid, the force per unit area on the piston on the left must equal the force per unit area on the piston on the right. In other words, F sub 1 divided by A sub 1 is equal to F sub 2 divided by A sub 2. A question on the MCAT could then be, you know the cross-sectional areas of both pistons, and you're also told the downward force on the left piston. You could then be asked what is the upward force on the right piston. Hopefully it makes intuitive sense to you that the piston on the right would move upwards. The size of the container has reduced due to the downward force on the left piston, and this liquid therefore pushes the right piston up. Moving on, I would now like to consider what is known as Archimedes' principle. To understand this, let us consider dropping an object into a fluid. As we know from real life, some objects will sink, whereas others will float. What determines whether an object sinks or floats is both the density of the object and the density of the fluid, how those two densities relate to each other. To exactly determine this mathematically, let us draw a force diagram for an object placed in a fluid. As this object has a mass, it has a weight force associated with it. There is a weight force pulling that object towards the center of the earth. Let us now assume that this object actually floats in the liquid. If the object is floating in the liquid, then this can't be the only force acting on the object. Again, if it was, that object would be pulled towards the center of the earth. There must be a force acting in the opposite direction, which is known as the buoyant force. This force is of course caused by the presence of the liquid. The liquid is composed of particles and molecules, and those particles are stopping the object from submerging into the liquid. If the density of the liquid is small enough, however, those particles will be very spread out, and that object can be submerged. Therefore, hopefully you can see why it is the densities that are important when determining whether an object will float or sink. Hence, as the object that is floating is not moving, we must have that the weight force is equal to the buoyant force. Archimedes' principle goes one step further. I hope you have seen yourself from getting into baths and dropping objects into liquids, that anytime an object is submerged into a liquid, the height of that liquid increases. The reason for this is of course again due to the particles. As we have placed an object into a liquid, that space that has been taken up by that object was originally composed of particles from that liquid. Those particles have to go somewhere, which causes an increase in the height of the liquid. More precisely, Archimedes' principle states the following. The buoyant force on an object that is submerged or partially submerged like a floating object is equal to the weight of the fluid that is displaced. By fluid displaced, I mean those particles within the liquid that had to be pushed or moved out of the way so that that object could be submerged or partially submerged within the liquid. In other words, the volume of the liquid has changed by let's say a height h, and the fluid displaced is that volume of fluid that has a height h. Hence, Archimedes' principle states that the buoyant force capital B is equal to the weight of the fluid displaced, capital W, and I've used Fd to represent fluid displaced. Recalling that weight is mass times acceleration due to gravity, we can replace this capital W with mg, and I've again used Ft to remember we're talking about the mass of fluid displaced, not the mass of the total fluid. As I mentioned in my introduction to density, it is quite common on the MCAT to instead be given the density or the volume. Therefore, we can replace the mass of the fluid displaced with the density of the fluid displaced multiplied by the volume of the fluid displaced. Note here that I have not written density of the fluid displaced, but simply the density of the fluid. This is of course because the density of the displaced fluid is the same as the density of the fluid. Density, remember, is an intrinsic property of a substance. The density of the fluid is the same everywhere. Therefore, the density of the fluid displaced is the same as the density of the rest of the fluid. To understand this better, let us consider a simple example. Let us assume that we have a block of mass m that is placed into water. Let's assume that when that object is placed into the water, that exactly half of that object is submerged in the water. In other words, half of it goes under the water and half of it stays afloat. The question could then ask us, what is the density of that block? To work this out, let us again use Archimedes' principle. We know that the buoyant force is equal to the weight of the fluid displaced. To determine the buoyant force, the left-hand side of the equation, remember the buoyant force is simply the weight of the block. Because the block is not moving, the upward force must equal the downward force. Buoyant force is equal to the weight of the block. Therefore, we can replace the buoyant force with the weight of the block, and again we can write the weight as rho vg, density of the block multiplied by volume of the block multiplied by acceleration due to gravity. This is the left-hand side. It is very common in these types of questions for students to get confused by this. Remember, I am still only looking at the left-hand side. I have not written down what the right-hand side of the equation is. I have only written down the left-hand side of the equation. Remember, the right-hand side is the weight of the fluid displaced. The right-hand side has to do with the fluid. The left-hand side has to do with the object. The buoyant force is to do with the object. In other words, all these quantities that I've written down, rho vg, have to do with the block and not with the liquid. The rho vg on the right-hand side, however, has to do with the liquid. It is the density of the liquid multiplied by the volume of the fluid displaced multiplied by g. As we have acceleration due to gravity's g on both sides, we can cancel them, and we are now left with the density of the block multiplied by the volume of the block is equal to the density of the fluid multiplied by the volume of the fluid displaced. How do we proceed from here? Well, we have not used the fact that we are told that half of the block is submerged. This means that the volume of the fluid displaced is simply half of the volume of the block. As half of the block is in the liquid, that same amount of volume within the liquid must have caused an increase in the height of the liquid. Therefore, we can replace the volume of the fluid displaced with half the volume of the block. Again, now we have the volume of the block appearing on both sides, which we can again cancel. We are now left with the density of the block being equal to the density of water, which again, remember, is 1000 kilograms per meter cubed or 1 gram per centimeter cubed, divided by 2. This therefore gives us 500 kilograms per meter cubed or 0.5 grams per centimeter cubed. In other words, recalling what specific gravity is, the specific gravity of this block is 0.5. Its density is half that of water. Hopefully you can see that this is actually quite a neat result. We can determine the density of a floating object simply by knowing both the density of the liquid and how much of that object is submerged within the liquid. Other types of questions relating to Archimedes' principle can be seen in the sample MCAT passages we have provided for you. I would now like to discuss what is known as viscosity. Some fluids flow more easily than others. The measure of the resistance of a fluid to flow is known as viscosity. To represent viscosity, we use the Greek letter eta, as I've shown here. The larger the value of this eta is, in other words, the larger the value of the viscosity, the larger the viscous drag is in that liquid. Viscous drag is a non-conservative force, just like friction. A non-conservative force, remember, means that the work done going from A to B is dependent upon the path taken. For example, friction is another example of a non-conservative force. Therefore, viscosity is a measure of this non-conservative force, this viscous drag. For example, what we would describe as thick fluids, for example, vegetable oil or honey, they are said to be very viscous. They have a high viscosity. Objects can move through these fluids, but they experience a very high viscous drag. On the other hand, thin fluids, for example, water and pretty much all gases, have a low viscosity. Objects can move through them very easily. Practically all fluids have some form of viscosity. However, we can approximate very thin fluids as having no viscosity. Such fluids are said to be inviscid. It turns out that the units of viscosity is pressure multiplied by time, in other words, Pascal seconds. Recalling that pressure is force per unit area, we can also write this as Newton seconds over meter squared. Typically in physics, we break up fluid flow into two different categories. The first type of flow is known as laminar flow. Laminar flow is a smooth and orderly type of flow. To visualize this, let us consider an object sinking in a fluid. As before, as that object is sinking, it has two forces acting on it. The weight force due to the object having mass, and the buoyant force due to that object being in a liquid. Remember, according to Archimedes' principle, as that object is sinking, the liquid surrounding it will be pushed up. For laminar flow, that movement of liquid is very smooth. That is represented in this diagram by these smooth layers that I have drawn here. Turbulent flow, on the other hand, is rough and disorderly flow. For example, we can consider a simple ball that is being held in the atmosphere. As the wind flows across that ball, the flow of that wind can, in some instances, be considered turbulent. Anytime there is turbulent flow, it can cause the formation of what are known as eddies. Eddies, as I have drawn here, are these swirls of fluid created as the fluid passes the object. In general, of course, this flow can also be laminar. What leads to a flow turning from laminar to turbulent is if the speed of the liquid is greater than what is known as the critical speed. Determining the critical speed is outside the scope of the MCAT, but you do need to know that it depends upon various properties of the fluid, for example, its viscosity. Anytime the speed of the fluid exceeds the critical speed, that flow becomes turbulent. Although you do not need to know how to derive critical speed for the MCAT, there is an equation regarding laminar flow that you do need to know. This equation results from considering laminar flow through a confined space like a pipe. For such a confined space, it is actually possible to calculate the rate of flow. This flow rate is determined by what is known by Poiseuille's law. To understand this law, allow me to draw a fluid going through a pipe. Let us assume that this pipe has a length capital L and a cross-sectional radius r. Let us assume that the fluid pressure at one end is P sub 1 and the fluid pressure at the other end is P sub 2. Let us also assume that the viscosity of the fluid is eta. The flow rate capital Q through that fluid is then approximately given as follows. Q is equal to pi multiplied by the radius to the power of 4 multiplied by the change in pressure, in other words P2 minus P1, divided by 8 times the viscosity multiplied by the pipe length capital L. On the MCAT, this equation is very rarely tested in full. Instead, a typical question on the MCAT could be, what is the relationship between the flow rate and the change in pressure? You would then say that this relationship is directly proportional. As you can see here, Q is directly proportional to the change in pressure. What do I mean by flow rate? Well, flow rate by definition is the volume of liquid flowing through the container per unit time. In other words, it is capital V divided by T. Hopefully you can see that capital V divided by T is the same thing as speed multiplied by area. Check that the units of both of these two things are the same. In other words, we can say that the flow rate is the same thing as the speed of the fluid multiplied by the cross-sectional area of the container through which it is flowing through. We can then ask what happens if that cross-sectional area changes. What happens to the speed of the fluid? A common example of this happening is when you push toothpaste through the tube. That toothpaste is initially in a large container, but then it is pushed through a small nozzle, a smaller area. It turns out that for a closed system, and I hope you remember what a closed system is, that the flow rate remains constant. In other words, the speed of the fluid multiplied by the cross-sectional area of its container remains constant. Therefore, if we have a container that is changing in cross-sectional area, as I have shown here, that if that fluid enters with a speed V1 through a cross-sectional area A1 and leaves through a nozzle that has a cross-sectional area A2, then that new speed V sub 2 can be calculated as follows. The flow rate remains constant and therefore V sub 1 A sub 1 is equal to V sub 2 A sub 2. Rearranging this, that means that that new flow speed V sub 2 is proportional to the inverse of the new cross-sectional area A sub 2. That means if the cross-sectional area decreases, the flow speed increases. I'm sure you've also seen something like this if you have a hole in a bucket. If you have water contained in a bucket with holes in it, then that water comes out of those holes very, very fast. This is because the cross-sectional area of those holes are very small. Now that we've considered the speed and velocity of a fluid, we can also consider the energy of a fluid. The energy of a fluid is fully described by what is known as Bernoulli's equation. If we again consider a container with a changing cross-sectional area, then we can also look at the changing liquid pressure. Let's assume on the left-hand side that the liquid pressure is P sub 1, it is moving with a speed V sub 1, and it is at a height H sub 1 from some reference point. On the right-hand side, let's say that the fluid has a pressure P sub 2, a speed V sub 2, and is at a height H sub 2 from that same reference point. Therefore here, I have not only allowed for the cross-sectional area to change, but also for the height of the fluid to change. Again, by the height, I mean the height from some reference point to the center of the container. If we approximate the system to being conservative, in other words the liquid has a very low viscosity, then the following is true. The liquid pressure plus a half of the density of the liquid multiplied by the speed of the liquid squared, plus again the density of the liquid multiplied by the acceleration due to gravity g multiplied by the height of the liquid h is a constant. This is kind of, as I already mentioned, conservation of energy for fluids. Let's look at each of these terms in turn. The first term is simply the pressure of the fluid. The second term, a half rho v squared, is known as the dynamic pressure, and it is the pressure associated with the movement of the fluid. The final term, rho gh, looks a lot like our pressure in a liquid term, and it is the pressure associated with the mass of the fluid. In other words, P, which we call static pressure, plus the dynamic pressure, plus the pressure associated with the mass of the fluid remains constant. Recalling that the units of pressure is Newton per meter squared, force per unit area, and that the units of energy is Newton multiplied by meter, then pressure can be considered an energy density. Newton per meter squared is the same as Newton meter per meter cubed, in other words, joule per meter cubed, energy per volume, energy density. This is why this equation is considered conservation of energy. In other words, if more energy is used to make a fluid move, in other words, if that dynamic pressure, the second term, increases, that pressure, that energy must have been taken from one of the other two terms. This is a conservation. An example of an application of this equation is with the Venturi effect. To understand this effect, let's consider the following container containing a fluid. On the left we have a container of cross-sectional area A sub 1, from which the fluid is moving at a speed v sub 1. On the top of this container we have a small opening that connects to a narrower container which also contains the fluid. We then allow this container to constrict in the middle and again have a narrow opening at the top. Finally, this container then returns to its original shape, its original cross-sectional area A sub 1. Such a tube is known as a Venturi flow meter. Note for this meter that the h in Bernoulli's equation remains the same. The liquid flows from left to right at the same height. Therefore, that rho gh term remains constant. What does change, however, is the speed. Recalling from the continuity equation that the flow rate remains constant, in other words, the speed multiplied by the cross-sectional area remains constant, the speed of the fluid through that narrow opening in the middle must increase. This is because the cross-sectional area decreases. Therefore, as the speed is increased, the half rho v squared term, in other words, the dynamic pressure term from Bernoulli's equation, must have increased. However, in order to have conservation from Bernoulli's equation, the static pressure, that capital P at the start, must have decreased. This decrease in the static pressure in the middle of the container causes less of the fluid to go up that narrow opening in the middle compared to the narrow opening on the left-hand side. This difference in heights in these two openings can be used to determine the pressure of the fluid. Another example of such an application of Bernoulli's equation is with the pitot tube, and the pitot tube is discussed in a sample MCAT passage that we have provided for you. Finally, I would like to finish off this topic on fluids by discussing fluid motion in physiology, more specifically with the circulatory system. In particular, I would like to state various properties of the circulatory system as they are applied to fluid motion. To begin, the circulatory system is of course a closed loop. There is no start or end point. Also, the fluid in the circulatory system has a non-constant flow rate. In other words, that capital Q does not remain constant. This can only be due to the fact that the fluid must be in some way viscous. It must have some non-negligible viscosity associated with it. This non-constant flow rate can of course be measured as a pulse. The pulse is caused by the fact that the flow rate is not constant. Also, of course, there is also a loss of volume from the circulatory system due to a difference between osmotic and hydrostatic pressures. Such fluid is eventually returned to the circulatory system in the form of lymphatic flow. Such occurrences mean that we can only apply the equations we have just derived in certain unique situations. However, what is true is that the blood volume entering the heart is equal to the blood volume leaving the heart. However, the viscosity of the blood in the circulatory system does not remain constant. There is a higher viscosity through each vessel as the blood gets further away from the heart. However, overall, the total viscosity of the circulatory system decreases with increasing distance from the heart. This is because, as we get further away from the heart, the blood vessels become more parallel, therefore creating a more laminar flow. Blood is of course pumped throughout the circulatory system by the squeezing and contracting of muscles in the heart. When there is the squeezing of muscles, the pressure in the heart increases, and when there is an expansion of these muscles, the pressure decreases. One final thing I would like to mention is heart murmurs. Heart murmurs are of course sounds caused by the motion of the blood across the heart. Unusually loud heart murmurs, which can be caused for example by defects in the heart, are heard because the blood flow has become turbulent. This is only one example of a fluid system in the body. There are of course other examples, for example the respiratory system. I encourage you to look up other systems in the body and see for example whether the flow in that system can be considered laminar or turbulent. As always, I would like to now finish this video by considering typical MCAT questions about fluid motion. To begin, this question asks us about specific gravity. If the specific gravity of a liquid is 3.5, which of the following is its density? Is it 3.5 kilograms per meter cubed, 35 grams per centimeter cubed, 350 grams per centimeter cubed, or 3,500 kilograms per meter cubed? Well, remember, specific gravity relates the density of an object or a substance to the density of water. Since the specific gravity of this liquid is 3.5, its density is 3.5 times that of water. Recall that I stated what the density of water was in two different ways. The density of water, rho sub W, is equal to 1,000 kilograms per meter cubed, or 1 gram per centimeter cubed. Again, I encourage you to check that both of these two things are the same. Therefore, the density of this liquid is 3.5 times either of these two quantities. It is 3.5 multiplied by 1,000, which is 3,500 kilograms per meter cubed, or it is 3.5 multiplied by 1, 3.5 grams per centimeter cubed. While 3.5 grams per centimeter cubed is not in our options, but 3,500 kilograms per meter cubed is in our options. It is option D. Therefore, the correct answer is option D. The next question is asking us about liquid pressure. It states that on Earth, what is the pressure of a liquid at a depth h? Is it equal to greater than or less than rho gh, or is it independent of the depth h? Well, let's recall why there is a pressure at all. There is a pressure at all due to the presence of particles. Above the liquid there is the particles within the air, and that causes atmospheric pressure P sub 0. In the liquid there is an additional pressure caused by the presence of the liquid particles. This pressure is given by rho gh, the density of the liquid multiplied by the acceleration due to gravity g, multiplied by the liquid depth we are concerned with, h. Therefore, the total pressure at a depth h in a liquid is equal to the sum of the atmospheric pressure and the liquid pressure. That atmospheric pressure is still there, but there is also this additional pressure. The total pressure is P sub 0, the atmospheric pressure, plus the liquid pressure, rho gh. Therefore, the pressure in a liquid at a depth h is going to be greater than rho gh. It is equal to rho gh plus atmospheric pressure. The correct answer is therefore option B. Next, we have a question which deals with Archimedes' principle and buoyancy. We are told that a metal bar has a weight of 20 newtons. When that metal bar is immersed in water, we are then told that its weight changes to 12 newtons. The question then asks us what is the density of the bar. Is it 900, 1300, 2100 or 2500 kilograms per meter cubed? Well, what does it mean in this question when it says that the weight is changing? Remember, the object has a weight purely due to the fact that it has mass. There is a weight force acting because that mass is in a gravitational field. That gravitational field has not changed just because the object is placed in a liquid. Instead, to understand this, let us draw a force diagram for this metal bar. This bar is in a container of water, and as before, as it is in a liquid, there are two forces acting on it. Again, it has a mass and therefore a weight which acts downwards. And because that liquid is resisting that motion downward, there is also a buoyant force upwards. Before, when we looked at this, we looked at an object that was floating. An object that is floating is not moving or accelerating, and therefore the net force on it must be zero. Remember, Newton's second law says F is equal to ma, therefore if the acceleration a is zero, the net force is also zero. We know that this is the case because the buoyant force was equal to the weight force. That upward force balanced with the downward force. However, this is not true for something sinking. For something sinking, the object is still accelerating downwards. However, that rate of acceleration is not the acceleration due to gravity. If you picture an object falling through the air and an object falling through the liquid, hopefully you see that the object that is falling through the liquid is accelerating less. This is because there is still a buoyant force acting upwards. This buoyant force is again caused by the particles within the liquid. these particles are making it more difficult for that object to accelerate downwards. However, when an object is sinking, the buoyant force is no longer equal to the weight force. If it was, the object would be not moving. Instead, what is true is that the buoyant force is less than the weight force. That means that there is still an overall force downwards, and therefore the object still accelerates downwards. It sinks. This is what is meant in the question when it says that the object's weight is changing. When the object is in air, we can approximately say that the only force acting on it is the weight. However, when it is placed in a liquid, there is both the weight force and the buoyant force. This causes the overall force to be less than the weight of the object. In other words, if I was to place a weighing scale in the liquid underneath the metal bar, that weighing scale will be less than if that weighing scale was placed outside of the liquid with the bar on top. Again, this is because overall the net force has decreased compared to the bar and the weighing scale simply being out in the air. Therefore, in the question when it says the weight has decreased to 12 newtons, that is of course not really what happens. The weight is still 20 newtons, but what we do say is that the apparent weight is 12 newtons. The apparent weight is simply the weight of the block minus the buoyant force. In other words, the net force on the block in the liquid. Hence, what do we know? We know that the weight of the block is equal to 20, and we know that the apparent weight, in other words, the net force, which is simply the weight of the block minus the buoyant force, is 12 newtons. Therefore, since we know that the weight of the block is 20, we can rearrange this for the buoyant force, and we get that the buoyant force is the weight of the block, which is 20, minus 12, minus this apparent weight. Therefore, the buoyant force is simply 8 newtons. Remember, Archimedes' principle states that the buoyant force is equal to the weight of the fluid displaced. Also, recall that we can write weight as rho vg, density multiplied by volume multiplied by acceleration due to gravity. Therefore, as the buoyant force is equal to the weight of the fluid displaced, it is also equal to the density of the fluid displaced, which is simply the density of the fluid, multiplied by the volume of the fluid displaced, multiplied by the acceleration due to gravity g. This is equal to the buoyant force, which we worked out as 8 newtons. We can now rearrange this for the volume of the fluid displaced, and we get that it is equal to the buoyant force 8 divided by the density of the fluid multiplied by the acceleration due to gravity g. How is this related to the volume of the block? Well, since the block is fully submerged, it is immersed in the water, the volume of the fluid displaced is simply equal to the volume of the block. As this block has sunk into the water, it has pushed a volume equal to that volume of the block away. It has displaced the volume equal to the volume of the block. Therefore, the volume of the block is also equal to 8 divided by the density of the fluid multiplied by the acceleration due to gravity g. How does this help us? Well, remember, we're trying to calculate the density of the block. Remember, density is defined as mass per unit volume, and therefore the density of the block is simply the mass of the block divided by the volume of the block. We don't know the mass of the block, but we do know the weight of the block. Remembering that weight is equal to mass multiplied by acceleration due to gravity, we can replace the mass of the block by the weight of the block divided by g. The volume of the block, as I just emphasized, is simply the volume of the fluid displaced. It is equal to this 8 divided by the density of the volume multiplied by the acceleration due to gravity g. Hence, as we have acceleration due to gravity g on the numerator and the denominator, we can cancel them. The density of the block therefore simplifies to the weight of the block multiplied by the density of the fluid divided by 8 divided by the buoyant force. Of course, from the question we know both the weight of the block and the density of the fluid. The weight of the block we're told is 20 newtons, and as this fluid is simply water, the density of the fluid is simply the density of water, 1000 kilograms per meter cubed. I could of course put in 1 gram per centimeter cubed, and then I would get the density of the block in grams per centimeter cubed. However, since our answers are in kilograms per meter cubed, it makes more sense to use the value of the density of water in kilograms per meter cubed. Working this out, we get that the density of the block is 2500 kilograms per meter cubed, and therefore the correct answer is option D. This next question again relates to the idea of buoyancy in a liquid. It states that an object of specific gravity 0.8, which hopefully you can say off the top of your head now means that the density of it is 800 kilograms per meter cubed, is placed into a container of water. We are then asked what percentage of that object is immersed in the water. Is it 20, 40, 70 or 80%? Based on these possible answers, we know that this object does not get submerged. It must float with some percentage of that object in the liquid. We are looking for the fraction of the volume of the block that is in the water. In other words, we are looking for the ratio of the volume of the fluid displaced to the volume of the object, the volume of the block. This is because the volume of the fluid displaced is equal to the fraction of that volume of the block that is in the water. Again, the fraction of that volume that goes into the water is equal to the volume of the fluid displaced. Therefore, we are immediately drawn to using Archimedes' principle. How will we introduce this? Well, since this object is floating, it is not moving, and therefore the buoyant force is balanced by the weight force. The buoyant force is equal to the weight of the object, the weight of the block. The buoyant force is given by Archimedes' principle. The buoyant force is equal to the weight of the fluid displaced, in other words, rho vg for the fluid. Therefore, it is equal to the density of the fluid multiplied by the volume of the fluid displaced multiplied by the acceleration due to gravity g. The right-hand side, the weight of the block, is simply the mass of the block multiplied by gravity, or the density of the block multiplied by the volume of the block multiplied by gravity. As before, the acceleration due to gravity's g cancel, and we can rearrange this for the ratio of the volumes, what we're looking for. The volume of the fluid displaced divided by the volume of the object or the volume of the block is equal to the density of the block divided by the density of the fluid. Of course, the ratio of densities is the same as the ratio of specific gravities. If we multiplied each density by the same factor, that factor would cancel in the numerator and the denominator. Therefore, the density of the object divided by the density of the fluid is simply the specific gravity of the object divided by the specific gravity of the fluid. We are told that the specific gravity of the object is 0.8, and of course, by definition, the specific gravity of the fluid, which in this case is water, is simply 1. Therefore, the ratio of the densities, and therefore, according to this equation, also the ratio of the volumes, is 0.8. The volume of the fluid displaced is equal to 0.8 times the volume of the object. Therefore, remember, the volume of the fluid displaced is equal to the volume of that fraction of the block that is in the water. Therefore, we can also say that the fraction of the volume of the block that is in the water divided by the total volume of the block is 0.8. In other words, 80% of that block is in the water. Again, hopefully you see that this is a very neat result. For an object that is floating in a liquid, the fraction of that object that is immersed in the liquid is determined by the ratio of the densities of the object and the liquid. For example, if an object has a density of 100 kilograms per meter cubed, that means that 10% of that object will be immersed in water. It is only when the density of the object is equal to or greater than the density of the fluid that the object will begin sinking. Finally, again, this question has to do with specific gravities and density. We are told that we have two different liquids. When equal volumes of these two liquids are mixed, the specific gravity of the mixture is 2. In other words, the density is twice that of water. Instead, when equal masses of these two liquids are mixed, the specific gravity of the mixture is 1.5. We are then asked what is the specific gravity of each individual liquid. Is it 1 and 3, 1.5 and 2, 2 and 2, or 3 and 4? Immediately reading this question, I feel like we are going to get two simultaneous equations. This is because we need to find two different quantities and we are given information in two separate sentences. Let us first look at the first sentence. The first sentence tells us the specific gravity of the mixture when we have two equal volumes of the liquids. In order to use this information, I'm going to use the fact that the sum of the masses of the liquids is equal to the sum of the mixtures. The reason I'm doing this is because I can then write those masses in terms of densities and volumes and then use the information from this sentence to simplify that down. Hence, we know that the mass of liquid 1 plus the mass of liquid 2 is equal to the mass of the mixture. Recalling that density is equal to mass per unit volume, I can replace these masses by density multiplied by volume. M1 I can replace by ρ1 V1, M2 I can replace by ρ2 V2, and the mass of the mixture I can replace by ρm Vm. It looks like we have too many variables in this equation. However, I'm looking at the scenario from the first sentence. In this first scenario, we know that the volumes of each liquid is the same. In other words, V1 is equal to V2. Therefore, I shall simply replace V1 and V2 by V. Therefore, we now have ρ1V plus ρ2V. And that is equal to the density of the mixture multiplied by the volume of the mixture. For the first scenario, we know that the specific gravity of the mixture is 2. In other words, the density of the mixture is either 2,000 kilograms per meter cubed or 2 grams per centimeter cubed. I've chosen here to write 2 simply because it's a smaller number, but in doing so I must remember that any other densities I calculate must be in grams per centimeter cubed. What is the volume of the mixture? Well, the volume of the mixture is simply equal to the sum of the volumes of liquid 1 and liquid 2. Since the volumes of liquid 1 and liquid 2 are the same, they are simply V, the volume of the mixture is simply V plus V. It is simply 2V. Therefore, each term in this equation has the same volume in it, and they cancel. This simplifies down to the sum of the densities of the liquids ρ1 plus ρ2 is equal to 4. Therefore, using only the first sentence, I have derived an equation relating the density of liquid 1 to liquid 2. My goal from here should be to also obtain an equation that has the densities of both liquids in it. In the second scenario, we are told information about the masses, so therefore I shall start this off by looking at the volume. Again, this is because when I look at the volumes, I can then replace the volumes by the mass divided by the density. Again, for a mixture, we know that the sum of the volumes of each individual liquid must be equal to the volume of the mixture. In other words, the volume of liquid 1 plus the volume of liquid 2 is equal to the volume of the mixture. As in our first scenario, I'm now going to replace the volumes by quantities that contain the density. In other words, I'm going to replace volume with mass divided by density. Therefore, instead of the volume of liquid 1, I now have the mass of liquid 1 divided by the density of liquid 1, and similarly for volume 2, m2 divided by ρ2. Likewise, this is equal to the volume of the mixture, in other words, the mass of the mixture divided by the density of the mixture. Again, why is this useful to us? Well, again, according to the second scenario, we have equal masses of each liquid. Therefore, we can replace m1 and m2 by simply m. Therefore, we now have m divided by ρ1 plus m divided by ρ2. This is equal to the mass of the mixture divided by the density of the mixture. The mass of the mixture is of course equal to the sum of the masses of each individual liquid. The mass of the mixture is simply m1 plus m2. Here again though, the masses are the same. Instead of m1 plus m2, we simply have m plus m. The mass of the mixture is simply twice m. For the density, we are told that for the second scenario, the specific gravity of the mixture is 1.5. Therefore, the density of that mixture is 1.5 grams per centimeter cubed. Again, as before, we now have the masses appearing in each term and they all cancel. Cancelling them results in 1 over ρ1 plus 1 over ρ2 is equal to 2 over 1.5, which I will write neither as 4 over 3. I've multiplied above and below by 2. Therefore, we now have two equations, equation 1 and equation 2, with two unknowns. Hopefully you are comfortable with solving simultaneous equations, but just in case I will go through it in detail now. There are many ways of solving this. The way I'm going to do it is by rearranging equation 1 for ρ2 and putting that equation for ρ2 into equation 2. In other words, I can rearrange equation 2 to give 1 over ρ1 is equal to 4 over 3 minus 1 over ρ2. Instead of 1 over ρ2, however, I will use the fact that from equation 1, ρ2 is equal to 4 minus ρ1. Therefore, 1 over ρ2 is 1 over 4 minus ρ1. I now have one equation with one unknown. This equation can be solved for ρ1. To do so, let me first move all of the ρ1s over to the left-hand side. So now we have 1 over ρ1 plus 1 over 4 minus ρ1 is equal to 4 over 3. And now I must add the two fractions on the left-hand side together. I hope you feel comfortable doing that. I can cross multiply, and doing so we get 1 multiplied by 4 minus ρ1, which is simply 4 minus ρ1, plus ρ1 multiplied by 1, which is simply ρ1. In other words, the numerator is 4 minus ρ1 plus ρ1. On the denominator, we of course simply multiply the terms, and therefore we get 4 minus ρ1 multiplied by ρ1. The right-hand side hasn't changed, and therefore it is still equal to 4 over 3. The numerator of the fraction on the left can be simplified because it contains minus ρ1 plus ρ1. The numerator simplifies to 4. To simplify this further, I can simply cross multiply the left and the right. In other words, we have 4 multiplied by 3, which is 12, is equal to 4 multiplied by 4 minus ρ1 multiplied by ρ1. In other words, 4 ρ1 multiplied by 4 minus ρ1. I can now divide both sides by 4 and get simply 3 is equal to rho 1 multiplied by 4 minus rho 1, which if I multiply out that bracket gives us 4 rho 1 minus rho 1 squared. This equation can be rearranged and we get rho 1 squared minus 4 rho 1 plus 3 is equal to 0, which is a quadratic equation which has factors rho 1 minus 3 and rho 1 minus 1. Therefore, the density of liquid 1 can either be 1 or 3. Hopefully my method for solving this equation was not too confusing. If it was, please use your own methods that you are comfortable with. We still have to calculate the density of liquid 2, and to do that we can simply use equation 1. When the density of liquid 1 is 1, according to that equation the density of liquid 2 is 3, and when the density of liquid 1 is 3, the density of liquid 2 is 1. In other words, the densities of liquid 2 are also 1 and 3. In other words, when the density of liquid 1 is 1, the density of liquid 2 is 3, and when the density of liquid 1 is 3, the density of liquid 2 is 1. Remembering that we are working in grams per centimeter cubed, this means that the specific gravities of these two liquids are also 1 and 3. We simply divide by 1. Therefore, the correct answer to this question is option A. As always, let us now recap what we learned in this lesson. I began by introducing the concept of density and how it is an intrinsic property of a substance. It does not change depending upon how much of that substance we have. The density is defined as mass divided by volume and has units of kilograms per meter cubed or grams per centimeter cubed. Specific gravity was then discussed, and I described how it is used to compare the density of an object to the density of water. It is simply the ratio of the density of that object to the density of water. I then reminded you about the concept of pressure, which is force per unit area. By its definition, pressure has units of newtons per meter squared, and instead of writing that all the time, we define that as a Pascal. 1 Pascal is 1 newton per meter squared. I then wrote an equation for the pressure at a depth h in a liquid. The pressure is equal to the density of the liquid multiplied by the acceleration due to gravity multiplied by that depth. This is of course only when there is no bulk motion in the liquid. This is only for a hydrostatic liquid. I then explained what happens when there is a change in pressure in a liquid. If there is a local change in a liquid at some point, that pressure change gets distributed throughout the liquid. This is known as Pascal's law. Then I described the forces that are exerted on an object that is either floating or submerged in a liquid. Anytime an object is in a liquid, there is what is known as a buoyant force. That buoyant force resists the tendency for that object to fall into the liquid. If the buoyant force is large enough, that object will float with only a certain fraction of that object in the water. However, if the density of the object is greater than the density of the liquid, then that object will sink. For either an object that is floating or sinking, I then introduced a way to calculate the buoyant force. The buoyant force is simply the weight of the fluid displaced. This is known as Archimedes' principle. One thing I did not discuss so far in this lesson is what is known as surface tension. Surface tension is the tendency for a liquid to act elastic on its surface. This is due to the attraction of particles in the surface layer of the liquid. Because of this, you can often see some insects that are very light and moving very fast walking on water. This is because the very thin top layer has similar properties to a solid. This makes the concept of an object floating more complicated, but thankfully this is outside the scope of the MCAT. All you need to know for the MCAT is that surface tension is a thing that can happen, and it is caused by the elastic tensity of the surface layer of the liquid. I then described how different liquids have a different resistance to objects moving within them. The measure of this resistance is known as the viscosity. This is a measure of the viscous drag force within the liquid. I then broke flows into two different categories depending on the size of this viscosity. Laminar flows were described as smooth and orderly, whereas turbulent flows were described as rough and disorderly. What determines whether a flow is laminar or turbulent is the critical speed of that liquid. I then looked at a particular laminar flow known as Poiseuille flow. This is laminar flow through a confined space like a pipe. For such flow, I introduced an equation that allowed us to calculate the flow rate. In other words, the amount of volume that passes per unit time. I then emphasized the fact that volume per unit time is the same as speed multiplied by area. In other words, the flow rate is the cross-sectional area of the container multiplied by the speed of the flow. For a closed system, I then stated that the flow rate remains constant. This is known as the continuity equation, and it explains why liquids tend to move at a great speed when they go through smaller openings or nozzles. For example, out of a toothpaste tube. Another example of this is a hose. I'm sure many of you as a child have held a water hose in your hand and placed your thumb over the nozzle. When doing so, I hope you noticed that the water seems to come out much faster. This is because you have reduced the cross-sectional area of the opening. In doing so, you've increased the flow speed of the liquid. This follows from the continuity equation. Bernoulli's equation was then introduced, which is simply conservation of energy for fluids. I stated that static pressure plus dynamic pressure plus the pressure associated with the fluid's mass must remain constant. Because of this, there is something known as the Venturi effect. This effect allowed us to calculate the pressure of a liquid using what is known as a Venturi flow meter. We can also use the same effect to calculate the actual fluid speed using a pitot tube, and this is discussed in a sample passage we have provided for you. I then finished this lesson by talking about fluid motion in our bodies. I focused in on the circulatory system, and I encouraged you to look at fluid motion in other systems, for example, the respiratory system. This video, in a sense, wraps up a very large discussion on fluids in general. We have looked at both gases and liquids, also looking at various properties of each, for example, temperature and the fluid speed. In the next video, we will start a new topic on electricity. As always, I hope this video has been useful to you, and I shall see you guys in the next one.